All right, so from the problems, number 4. Now, of course, we get some of this information from problem 3, right? So from problem 3, we know that a human, the average human, is going to radiate at 310 Kelvin, and therefore the maximum. So this is really just kind of finishing up problem 3. The maximum wavelength is 9.35 times 10 to the minus 6th meters, and from that table, I think it's 3.8, that gives us that tells us that that's in the infrared region. All right, let's continue with let's do actually problem 4 using this temperature, 310. All right, so this F here is equal to sigma times the temperature to the 4th power. So F is the it's what we would call the power flux. Okay, flux is the amount of power produced per square meter. Okay, sigma, this symbol right here is sigma, is called the Stefan-Boltzmann constant, and then the temperature has to be in Kelvin, which of course our temperature already is. Right, so this is sometimes called the Stefan-Boltzmann law, and I will often refer to it that way. So in this particular case, it's going to be sigma, which is just a constant of nature. Stefan and Boltzmann, who actually knew each other, came up with this value. This is a constant of nature, and the value of it is has been measured very, very accurately. It's 5.67 times 10 to the minus 8th watts, and the units are a little funny, watts per meter squared, and times Kelvin to the 4th, where the Kelvin to the 4th is also in the denominator. All right, so let's multiply. So we're just multiplying these two numbers. Now make sure you know how to raise something to the 4th power. All right, so why did I wrote 318? I don't know. Hold on. All right, sorry. This should not be 318. This is 310. Sorry about that. All right, let's go back to this problem. I think I've all right. So this is 310. I don't know why I wrote an 8 right there. All right. So the key thing about this particular problem and doing this problem and coming up with this correct number is to raise this 310 to the 4th power, and then of course multiply it times 5.67 times 10 to the minus 8th. So make sure you know how to do that in your calculator. With the one that I'm holding in my hand, the Texas Instrument, you just use the little up arrow key or the caret key. So I type in 310 caret 4, right? And so that raises 310 to the 4th, and then you multiply it by this constant, the Stefan-Boltzmann constant. So then you get, for this particular, for a human, for the average human being, because they have this temperature, 310 Kelvin, they are putting out this much power per square meter, so 523.6 watts per square meter. Now the problem with that is it says, number 4, very specifically, I'm looking at it right now, it says estimate the total amount of energy you radiate to your surroundings. All right, well, the thing is, this is power. Watts are units of power, but power is just energy per unit time. And a very typical thing that we do is you say, okay, in 1 second, what would be the amount of energy? If this is the power, which is the amount of energy per unit second, right? So that's what power is. It's the energy per time, and the time is usually typically in seconds. For that to happen, you usually just say, okay, in 1 second, the energy would be, and by the way, energy is measured in joules. They're called joules. So joules per second is also known as watts. And people more than likely heard of watts because, you know, light bulbs are measured in watts. It's the amount of power. But if you know, like for example, if you took a 60-watt light bulb and you asked yourself how much energy in 1 second is that light bulb emitting, it would be 60 joules. So in this particular case, the amount of energy that the average human emits in 1 second is 523.6 joules, and it's actually the energy flux. All right, so it's the energy per square meter. All right, and so 523.6 joules per square meter. All right, let's do the next problem. All right, so number 5, let me read that. It says the sun has a temperature of 5,800 Kelvin, and its black body emission peak has a wavelength of approximately 500 nanometers. By the way, that's yellow light. That's why we have a yellow sun. At what wavelength does a protostar, we'll talk much more about protostars later on in the semester. Anyhow, at what wavelength does a protostar with a temperature of 1,000 Kelvin radiate most strongly? Okay, so for that, we're going to use this thing called Wien's law, which we used before. Remember, lambda max is equal to 2.9 millimeters divided by the temperature in Kelvin, where lambda max, if you do this with your telescope and a detector, of course, you would find the maximum wavelength, the peak wavelength on a black body curve. This is called a black body curve, the intensity versus the wavelength. Anyhow, once you actually see what that is, so that's something you measure. So in this particular case, you would measure this, of course, from a hot protostar, but this one they're saying, okay, well, if the protostar was 1,000 Kelvin, what would be the peak wavelength? And then you could verify it like experimentally. All right, so anyhow, let's take a look at this. All right, so lambda max is going to be 2.9 millimeters. Okay, so that's you always use that constant with Wien's law. This time it's divided by 1,000 Kelvin. All right, so that's pretty simple. It just becomes 0.0029 millimeters. All right. Now you want to change millimeters. So let's change the milli part to times 10, using our metric prefixes, which I talked about a little in the last video. Milli means times 10 to the minus 3. So you can just simply replace the metric prefix with times 10 to the minus 3. So to put it into sign, if I'd put 3 more zeros in front of this decimal place, and then to turn it into scientific notation, you'd move the decimal point behind the 2, so it's 2.9, and then because there's 6 zeros in front of that, that would be 2.9 times 10 to the minus 6 meters. All right, so that would be that would actually, but by the way, just to let you know, it doesn't ask us this, but so that's the wavelength that it emits most strongly. That's actually in the infrared, just to let you know. All right, let's move on to the next one. All right, so number 6, let me read it. It says 2 otherwise identical objects have temperatures of 300 Kelvin. That's the one I'm going to call object B here, and then and 1500 Kelvin respectively. Which one radiates more energy, and by what factor does the emission exceed the emission of the other? Okay, so right away, like if you look, of course, the amount of energy per square meter, also known as actually it's power per square meter, is given by the Stefan-Boltzmann law. So F is equal to sigma, which is I said in a previous video, of course, that's the Stefan Boltzmann constant times the temperature to the fourth. All right, so since they're asking us to compare one object to the other, again, we'll call the object that is that has a temperature of 1500 Kelvin, that's going to be object A, and then the 300 Kelvin will be object B. All right, so the way that you do that is you just say FA divided by FB. All right, so the power flux, that's actually what this is, of A divided by the power flux of B. Notice the sigmas cancel, right? And so it's really just the temperature of A raised to the fourth power divided by the temperature of B raised to the fourth power. All right, so there it is. Okay, so there's the calculation. Try this in your calculator if you haven't done so already. Pause the video if you need to. So this is important to be able to do this. You know, raising something to you got to know how to raise something to the fourth power. With my calculator, you use the caret key. If you have any problems with that, make sure you come to my office hours for that kind of thing, okay? Because that's really important that you know how to do that. Anyhow, when you do divide 1500 to the fourth divided by 300 to the fourth, you get 625. So notice this is the power flux of A divided by the power flux of B. And so if I bring, you know, just think of this as an equation. If I bring the B to the other side, that tells me that FA, the power flux coming from the 1500 Kelvin temperature object is 625 times the temperature coming from the power flux coming from the 300 Kelvin object. All right, that is problem number 6. Problem number 7 deals with what's called the Doppler shift, also known as the Doppler effect. Okay, so it goes by two names. It's this equation right here. So let me go over what this actually means. And now this equation, of course, c is the speed of light. If you have something that is, you know, the Doppler shift or the Doppler effect, it goes by either name. Works also for sound waves and you know any other type of wave phenomena, and so the velocity down here in the denominator would be the velocity in the medium that you know when there's no motion between the observer and the source. All right, so this is specifically for light because you know that's what we deal with in astronomy. All right, so let me go over this. So you got lambda minus lambda naught. That's how you say this when lambda sub 0 or lambda naught is equal to the change in the wavelength. And let me go over this real quick. So if the change is positive, all right, that is the wavelength. The moving wavelength, by the way, lambda is the moving wavelength, lambda naught is the wavelength at rest. If the moving wavelength is greater than the resting wavelength, then this delta lambda is positive, and that's said to be blue shifted. All right, that's supposed to be an L. So that's blue shifted, or in other words, the source of the sound, or sorry, it's in this case we're talking about light, but it's either way. The source and the observer are moving towards each other. All right. So if the wavelength, like for example, a really good example of this is like if it's not really talking about wavelength here. It's talking about the pitch. But you know, if you hear a siren. And the siren is moving away from you. The pitch is you know, it's lower, right? Like it's higher frequency if the thing is approaching you, and so the same thing happens to the wavelength, right? Well, actually the opposite thing. If the wavelength if the wavelength of the moving object is smaller, and the reason the wavelength changes is because there's relative motion between the observer and the source. All right. So again, it doesn't matter whether it's water waves or sound waves or light waves. All right. So anyhow, if if the source and the observer are moving away from each other, then the moving wavelength, just what we call lambda, is going to be smaller than the wavelength at rest, right? If this is like, sometimes we call this the wavelength in the laboratory. If you were at rest,